Okay, wait. So I'm going to show you real quickly, and you don't have to learn this now, but here, for example, how do you do stoichiometry? Blah plus blah yields blah. There you go. There's an equation, right? And you know that if you had something like grams or anything besides that, you could change that into moles, and you already know how to do stoichiometry, right? But this equation, this chapter, one of the big equations is this one. Molarity equals moles, and you don't have to write this down yet, solute over liters of solution. Now, if you were to take that equation and rearrange it, it would look like this. Molarity times volume in liters equals moles. So, imagine doing the same kind of problems you did last chapter, except I do something like this. 50 milliliters of 0.01 molar copper 2 sulfate are used to react with 20 milliliters of 2 molar aluminum chloride. Now, so you say, well, how do I do that problem? And I'm not here to teach that right now. I'm not here to teach it right now, but think about this. If you know the molarity, and there it is right there, you can plug that into here. If you know the volume in liters, that says 50 milliliters, that would be 0.05 liters. Is that correct? If I know the molarity and I know the volume in liters, what does that give me? Moles. And where can you go in stoichiometry? You can go directly into the mole world, just like that. Now, unfortunately, if I tell you how many moles there are of that one guy, and I tell you how many moles there are of this guy, what do you have to do? What kind of problem is that? Limiting. But see, we've done that, haven't we? So it's not that big of a transition between knowing molarity and volume and get into moles. That's not the big transition for this chapter. So we will do that several times, but that's kind of neat how that all works together. If molarity times volume gives you moles gives me right into the mole world, I'm ready to go. And if you can do these problems, you can pretty much do almost any stoichiometry problem they're going to have, certainly the first semester maybe in college. Okay, well, what I want to show you is we're going to be doing a chapter on solutions. And so this is the same handout I used in 10th grade. So I want to go over it again. And the first thing is, do you know what a solution is? And a solution, do you remember that great big chart? And it said pure substances, mixtures, remember that? I happen to be doing that in the 10th grade right now. Remember that? Everything's made of matter, and matter can either be something that has the same composition as a pure substance, or it can be what? A mixture. And what if you're a pure substance? You'll be an element or a compound. What if you're not on the periodic table? And what if you don't have a chemical formula? You must be a mixture.
Is that just a chart you have? Or is it in our handout?
No, this is one I use in 10th grade. That's not this chapter. I just said, do you remember when we did that? We did the classification of matter. And then guess what happens? There's two kinds of mixtures. One mixture, when you look at it, it looks like everything's the same. And what do you call those? Solutions. See that? So the world you're in is in the world of mixtures, which are called solutions. And solutions are homogeneous mixtures. Okay, good. Now, mixtures can be made many ways. All right. So we have to have a way of figuring out, hey, did you make your coffee real strong today or not so strong? Did you make your sulfuric acid really strong today or not so strong? And so we have different ways of telling us how concentrated this solution was. Now, do you know, what do you call the stuff that gets dissolved? What do you call the stuff that gets dissolved? If I put a little bit of salt in a lot of water, The salt, and I make salt water. What would you call the salt? Solute. And what would you call the stuff that does the dissolving? What is it? Solvent. And what do you call it when you solvent or solute and solvent come together? You put them together. It's a solution, isn't it? Now, it just so happens that chemists decided that they needed a way to describe how concentrated a solution was. Now, this is where you have to be careful, and you're 12th graders, so I don't have to spend as much time with you as I did the 10th grade, but concentration is a ratio, isn't it? So you got to be careful. Look at these three pictures. Big, not so big, small. But who's the most concentrated? Which one's the most concentrated? So see that size there? If you want me to compare, I'd have to draw the same size box in all three cases, wouldn't I? Now, who has the most stuff dissolved in the same amount of volume? This guy. Now, let me ask you this question. Which one is more concentrated, this much of this material or all of that material? Which one's more concentrated? And even though you're 12th graders, you get fooled a little bit because it's a ratio. It's a ratio. You get that? Now, try it again. Which one's more concentrated? All of this or all of that? C. Okay, what about a drop of this and an ocean full of this? Who's more concentrated? Okay, it's still C, isn't it? So that's why you got to be careful with that guy. Now, which one will contain more solute? A drop of this or an ocean of that? Please, an ocean of this would have a huge, huge amount of solute, wouldn't it? But that's not what if I ask about concentration, though, any amount of that is more concentrated than any amount of that, right? All right, so everybody got that? It's a ratio, isn't it? All right, bad news. Bad news. How many ways can you represent concentration in chemistry? I wish it was what? I wish it was only one. And I will tell you the good news. Almost all the chemists use this guy. This is the star of the show by far. When I eventually get there, when we get to molarity, you'll say, I should know molarity the best. That's the good news. Molarity is used more than any other concentration. Now you say, why are you teaching the other then? It won't go away. It doesn't go away. There's one chart. Look back there, Jeb. See that? Point to that chart that's white and blue. Can you, you see it? Okay. Can you read what the x-axis said?
Temperature.
Okay, temperature, and what's the y-axis say?
Grams of solute.
Keep going. Grams of solute.
100 grams of water.
All right, you know what? Somebody said, hey, when I put this in there and stir it, it dissolves. When I put the same amount of another chemical in the same amount of water, it doesn't dissolve. And they said, I'm going to call that solubility. And how am I going to measure solubility? I know. It's how many grams can I put in there per what? Per 100 grams of water, which is 100 milliliters, isn't it? And that's what that chart says. And you know what? I think that's the only time they ever use that concentration unit. What is it again? Grams of solute per what? So I can see them setting up the experiment. 100 milliliters, 100 grams, 100 grams of everything. Chemical number 1, chemical number 2. See that? That's how they did the experiment. And so this is not to be, you can't ignore it because it's in every chemistry book. And somebody decided, I'm going to measure the concentration, the solubility concentration in grams of, I'll put that down, grams of solute per 100 grams of solvent. Now, that's about the only time I see that concentration unit used. You ready to move on? Are you ready to move on? Okay, we're not going to emphasize that. It's going to be, you're going to see it. When you see that graph, you'll say, that's when I'm going to use it. Other than that, I'm probably not going to use it. Next one. This one is called a percent by mass, which you guys are really good at. And you know what? I used to do this. Here it is. Grams of solute per 100 grams of what? No, not solvent. What is it? Solution. Okay, so we're going to make some little solutions here in a minute. And I find this. I was actually a biology major in college. They made me take 5-6 semesters of chemistry to get my biology degree. And so that's why I picked up chemistry later on. But all the time in biology, we were doing something like, okay, let's make a 10% salt solution. Let's make a 20% salt solution. And that's what biology did all the time. And how do you do that? I'll show you how to do it in just a minute. But think about that. If you make 20%, if it's grams of solute and grams of solution, what big 4-letter word do you not even have to think about that they use in chemistry all the time? What 4-letter word in chemistry is not even you don't even have to know what it means to make these solutions? Mole. You could be a biologist and say, well, I took some chemistry, but I don't like that chemistry stuff very much. And you know what? You don't even have to know what a mole is, and you can make these solutions. Now, I'm not trying to tell you that biologists aren't smart. There are a lot of smart biologists. You get that? But it's funny that they still make their solutions in percent by mass. Here's another one. This is percent by mass also, except percent. What does percent mean in Latin? I never took Latin, but per 100. And what does this say? This is parts per 100. That's percent. What's this say? Parts per what? Now that is used in science a lot, ppm. And if you become a real famous scientist, a chemist, and you travel the world, you're an environmentalist, you'll probably be testing for certain kinds of chemicals, and some of them are so toxic that you have to measure them at the parts per million level. There are some that are even more toxic than that, called parts per billion, and whoa. Now you're talking about something that is really toxic, parts per trillion. I need to know when there are parts per trillion in the environment, because you get too many of them, it's going to kill people. Now, plutonium would be one of those. You don't mess with plutonium. You have a lot of plutonium in one place, you're going to kill people. Another thing about this chapter that I really like, we can't wait in our oceans. We can't wait until all the fish come up dead and said, I think we were doing something wrong there. We were putting something in the ocean and all the fish are dead. That's too late. We have to be able to measure these chemicals when they're in solution at a low level and know, are they going up or are they going down? And that's why this chapter is very important. The solutions, most chemists do their analyzing in a solution. And that's what makes this chapter, I think, even more important for you. So these all fall in the same category of mass over mass. Isn't that right? It's like mass per 100 grams of solution, mass per 1,000,000,000 grams of solution. Get it? That's the same idea. The mole idea doesn't even come in, does it? Now we go over here, and I'm going to jump over this molarity guy, the star. Molality. You know, I had to give them a lot of credit. They eventually said, you know, this mole thing, this is important. And they said, but yeah, we always made our solutions like the biologists did. And now you're saying we have to make them based on the mole? Well, okay, but moles of solute, not grams anymore, moles of solute per what? Per kilogram, that's liter of like water, right? Per kilogram of solvent. Wow, that's weird. That's kind of like this guy, isn't it? And you know what? Will you ever use molality ever in freshman chemistry? It's possible, but it's going to be minor. It's going to be minor. All you have to do is go back, look up the definition again. I got it. It's minor. Everybody get that? Will I ask you one question on it? I might. Get it? Okay, same thing with normality. I won't even talk about normality in here, okay? And maybe your chemistry class will talk about it, maybe they won't. It's very possible they won't even talk about normality, so I'm probably not going to say very much about that one. And this guy, percent by volume, that's the same idea here. Volume of solute over volume of solution. Get that? That's percent. And we're going to make some, I'm going to show you how to make some solutions. And I don't know if I could listen to myself when I was your age. I don't know what. At least, you guys are at least nice enough. You think, man, this is the third year I've had that teacher. It's getting tough. But I'm going to just mention to you, I don't know if I can listen to myself for 3 years like you have, but I kind of wish I would have taught what I'm teaching you. You get that? And I wasn't. I wasn't taught this stuff. I couldn't be the chemistry student you can be. You can be the chemistry student you need to be if you want to. I had very little of this and went to college. I was like, what is going on? It was like I was trying to keep my head above water all the time. I was never ahead of the game, never. And I didn't have the tools that it took. And this right here, even this, I'm going to show you these lessons here. You guys, by not understanding this right here, this is simple. I'm going to show you how to make solutions. That's another thing I'm going to mention. I was never allowed to make my own solutions. I thought that was a teacher's job. We got ready to do a lab. Guess what the bottle? 2 molar copper 2 sulfate. Okay, thanks. Thanks for making it for me. I don't know how to make it, but you're the teacher. And then I went to college, and guess what? They made it for me. They made the solutions for me. Huh. Guess what happened when I first started teaching? There was a teacher who had been there a long time. You know what I asked him to do? Could you make this solution for me? Oh, yeah. And he did that for a few years. And after I started teaching chemistry more, I started thinking, this is not right. I'm a chemistry teacher. Why, just because I've never made solutions, I should be able to learn how to make them. And that's what I want you to do. All of you are going to learn how to make your own solutions. You're going to be way, way above where I was at, way above. And when we do our labs, you're going to make them. If you make them wrong, your lab's going to come out wrong. You make them right, then they come out right. So I hope you can be excited about this. I want you to be able to do this. I want you to go to college and say, yeah, I can make that. Well, we made our own solutions. You're not bragging. You're saying, I understand how to make them. So what I'm going to do here is, let's go to, whoops. Wow, I don't see it. I'll make one up. Okay, so what I'm going to do is, let's make some solutions, okay? I thought I included that. I guess I didn't. I will look for that, and I'll go ahead and do this way today, but I thought I had a handout sheet on this. Let's do this. I'm getting ready to do a lab, and what I need is, I need a 10% sodium chloride solution. And my lab, I figured out that I'm going to need about 800 grams of solution when you get done. Okay, so what we're going to do is we're going to look at the mathematics of it, and then we're going to look at how do you actually make it. So let's do the math over here. Okay, now, whenever you see 10% salt solution, then the salt is the solute and the water is the solvent. Is that correct? Okay, so let's do the math. 10% of the solution has to be salt. So how do we do that? 800. When I get done, I'm going to have 800 grams of this stuff in front of me, aren't I? How many grams of that is going to be salt? Isn't it going to be 10%? What's 10% of 800 grams? Help me out. I need 80 grams of NaCl. I'm going to get my balance out. I'm going to put 80 grams in a container, 80 grams of NaCl, and then what am I going to do? 80 grams of NaCl, and how much water am I going to have? This is the easy part. How much? Oh, 720? Okay, so now, step by step. If I took a video of you making this solution, what do you see yourself doing? Let's put somebody on the spot. All right, you're on the spot, okay? I'm watching you, got a video. Tim, I want you to make this for me. What are you going to do first, Tim?
Do I get my...
Tim, we're wasting time. Tim,
weigh the tear mass of the...
Okay, all right. So you want to put a beaker on there and zero it out by subtracting the weight of the container, right?
Well, I probably need something more exact to measure the water with, but yeah, measure the weight of the...
How much?
Would it be an ounce? I don't know how much is it?
Wait, where did ounces come from?
Or would it be...
Wait, you started off so well. Let's try it again. All right, we're going to start the video again. Okay. Tim, how do you make this solution? You're going to go to balance and put a beaker on it, right? And then you're going to press the auto tear feature. And now it reads 0. Now what are you going to do?
I take that back so that I filled up the water.
No, not yet. Let's not do that yet.
Don't I want to get the water first?
Well, that's a good question. I could do that.
I'd fill it up with salt.
How much?
I would fill it up with mostly a random amount. But
Wait, let's try again. We're not making a random solution. We're making a very specific solution.
no, but I can adjust it at the scale.
Okay, so I've zeroed out the beaker, and I've got the salt in my hand.
Yeah.
Now what am I doing?
Well, I would need to know. I would need to put a certain amount in, and then
A certain amount? Wait,
I would need to weigh
wait,
that certain amount
wait,
to see
wait.
how much that amount weighs.
Well, how much do we want?
We want 80 grams.
That's right. So you're going to mass out 80 grams of salt in that beaker, right?
Okay. How do I know that I'm putting 80 grams in? It's on the scale.
Okay, I'm on the balance. And you already zeroed out the beaker. You zeroed out the beaker, and now you got the salt in your hand, and you keep putting it in there. It says 70, 75, and it gets to 80. You said, stop. 80. Now what am I going to do?
I would take that back, and I would get a new
Okay.
and then I would tear that weight, the weight of that beaker, and I would fill the beaker up with...
Fill it up?
Well, yes.
You're making this difficult. What if it's 1,000 milliliter beaker? Are you going to fill it up?
I was going to say fill it up with 720.
You're going to add.
Yeah.
All right, now we're getting there. So you're going to mass out 720 grams of water. You're going to mass out 80 grams of salt. And then what are you going to do?
Mix them. And once it's mixed with...
Okay, right? So now we have, we put them together and we mix them together. And later, when you guys make your own solutions, I'm going to let you use a really neat little thing called a stir station. And what you're going to do is, it's going to be a little box you plug in. And you probably saw this in 10th grade, but you put a beaker in there. And I have these plastic coated magnets that sit there. And underneath here, you won't see it, but there's a motor in here. And the motor's attached to another magnet underneath in the box. And when you turn the little dial on the front, it'll make this little magnet in the box go around like that. And the magnet you have in the beaker will go around like that. And so what will happen is you turn this on and you can go do something else and just let it'll keep stirring it for you. See that? Until it's all ready. I can't wait till you guys start making your own solution. I want you to. Okay. What do you think about that? would you have any trouble making a percent by mass solution? So if you're a biologist, you can see how this is pretty simple, isn't it? What's the only piece of equipment I really need? A balance. Matter of fact, if I didn't have a beaker, could I use a bowl? I don't need any special equipment except for a balance. Let's make another one. Okay, here we go. I want you to make me a solution that is 20% by volume methanol. Now, you don't know what methanol is, but I'll show you what it is. Methanol is this. That's the chemical for methanol. And in second semester, we're going to do organic chemistry, and you'll see that. You say, that's methanol. Okay? And you'll know everything about methanol. All right. So, let's do some math first, and then we'll talk about how to do it. And so who wants to tell me how to do the math here? Who wants to do the math? All right, Calvin.
You take 750 milliliters.
Say it again.
You take 750 milliliters. You times it by 0.2 to get whatever number that's going to be.
So what is that number?
That'd be
150? Okay. Okay, so what do you want to do? All right, I'm going to put you on a video. All right, Calvin's going to show us how to make a 20% volume by volume methanol solution, and we need 750 milliliters total. All right, I'm ready. Go, Calvin.
So I would mass out 150 milliliters.
Now, how do I mass out milliliters?
No, 1 milliliter is the same as 1 gram.
If it's water.
I would have to know the conversion.
Huh? How would you do that? What are you going to do? You're going to measure volume. You know anything in this room that measures liquid volumes? Thank you, Jim. What? One more time. Oh, I'm sorry. Make the screen bigger? Or you want to go high? What?
Like zoom it in.
Zoom it in? Oh, okay, I'm sorry. I see. I'm sorry. Zoom in. Okay. How about that? All right, Calvin, I'm ready.
Graduated cylinder.
Start the video again.
I would measure out 150 milliliters of methanol in a graduated cylinder.
Ah. You have to picture yourself doing that, and I do picture yourself doing that. And you remember about the meniscus? You read the bottom of the meniscus, and you're doing a good job. Now what?
Then I would have to add 600 milliliters of water to that. And then stir it. And then I'm done.
What do you think? Isn't this the same idea? Percent by mass, solutions percent by volume. They're kind of, I can do these. And notice that we didn't have to go into the mole world, did we? And so it's nice that you can do both of these. You may run across this. If you take a biology class, you may run across somebody saying, oh, that's a 15% by volume of such and such. See that? Can I ask you a quick question? This is a way off the subject in a way. Do you know, what word do they use when you dissolve something in water? It's not off subject. If you dissolve in water, it's called a blank solution. What do you call it if something's dissolved in water? aqueous. Do you know that what if you dissolve something in alcohol? You know what it's called? And it's an old-fashioned term, which I never knew until, when I started teaching. If it's dissolved in water, it's called an aqueous solution. But if you dissolve in alcohol, it's called a tincture. Tincture. Have you ever heard of that? A long time ago, when I was really, really young, usually it was the grandmother who had this, and some parents had it too. They had a little bottle in their medicine cabinet, and it was called tincture of iodine. What's that? And when you got a cut, they were so afraid that bacteria might get in there, they wanted to put something in there that would kill any bacteria. See that? So they get this little bottle out and had a little brush on it. And it made your skin turn colors like orange. And it was called tincture of iodine. And you know what? It hurt. Why did it hurt so much? Yes, it was dissolved in alcohol. Yes, that hurts on a cut. Okay. We'll start this one. If I don't get finished, then we'll see. I need 800 milliliters of 0.5 molar NaCl solution. Okay. Now, this is where we enter the world where almost all chemistry lies in, okay? And this is a big M, and I'm going to show you what that means here. This is the equation, molarity. By the way, all these are concentration units, aren't they? Percent by mass, percent by volume, molarity. They're all concentration units. Molarity equals moles of solute over liters of solution. Is everybody with me on that? That is the star of the whole chapter. Get that? So, can somebody help me make this solution? We'll do a little bit of math, and then we'll do some. How about somebody just take a chance? Let's take a chance. Gabby, you take very many chances? Take a chance, Gabby. Tell me how to make this thing. Let's do the math first.
Okay, so if it's 0.5.
Can I give you a clue?
Yeah.
That capital M is molarity. And capital M also means moles per liter. Okay, that might hint you a little bit.
So you would have 0.5 moles.
Not moles. That's the molarity is 0.5. Where do I put this in the equation? Where can I put this number? Here, here, or here? Wait, there? Here?
Yeah.
That's right.
And then you have 800 milliliters or 0.8 liters.
800 milliliters, but I can't put it here because that says liters.
You need 0.8
Yes,
liters of solution.
not water.
And then you're
Ooh,
solving.
you're going to solve for X? Okay, let's try that. What do you got there?
So
What's 0.8 times 0.05?
is it 0.5 or 0.05?
Whoa. What is 0.5 times 0.8? I bet it's half of it, isn't it? So, what am I doing? The moles that I want, I need 0.4 moles. Now, I'll show you, if you had to show your work, let me show you how this works. Molarity is moles per liter. What's moles per liter times liters? What's moles per liter? Moles per liter times liters. It gives you moles, doesn't it? But big M is not moles. Big M is molarity. Now, we're almost ready. We've done the math, and we're almost ready. Tell me what to do first. I'm ready, and okay, you're on video. Gabby, please make me 800 milliliters of 0.5 molar NaCl solution.
So you multiply the molarity by the, or,
Tell me what to do. It's a cookbook show, okay?
okay,
Hello, I'm Gabby. I'm going to show you how to make this solution. The first thing you're going to do is,
you get 0.4 moles of NaCl.
how much is that? I'm watching a cooking show. I don't know how much that is. How much is that? How do you do this? If you had moles, right? Moles. What's the shortcut? Moles times molar mass gives you grams, right? So what's the molar mass of NaCl? Okay, 35.5 plus 23. How much is it? 58.5 grams per mole. That'll cancel out. And tell me what you get there.
Attention DR students, student athletes, and student drivers may now
All right.
be dismissed.
We'll start right there. We'll start there, Mark. Okay, thank you.
Please do not